Welcome back to the energy conversion lectures. In a previous lecture, I have covered some introduction about the inductance and some derivation of a single coil magnetic circuit. In this lecture, multiple coils magnetic circuit will be studied to derive its inductances. Assume we have a magnetic circuit consists of two coils as shown. As I mentioned in a previous lecture, the magnetic field lines produced by each coil can be divided into two components: a leakage magnetic field component and a magnetizing magnetic field component. Therefore, the current I1 flowing through coil 1 will produce two components: phi L1 representing the leakage magnetic fields and phi M1 representing the magnetizing magnetic fields. Likewise, the current I2 flowing through coil 2 will produce two components: phi L2 representing the leakage magnetic fields of coil 2 and phi M2 representing the magnetizing magnetic fields of coil 2. The direction of each magnetic field component is determined by using the right-hand rule. Based on these magnetic field components, we can determine the magnetic fields that links each coil. Therefore, the magnetic fields that link coil 1, represented by phi 1, are equal to phi L1 plus phi M1 plus phi M2. The magnetic field phi M2 in this equation is considered a mutual magnetic field between coil 1 and coil 2 because it is produced by coil 2 and linked coil 1. Now let's move on to coil 2. The magnetic fields that link coil 2, represented by phi 2, are equal to phi L2 plus phi M2 plus phi M1. Again, the magnetic field phi M1 in this equation is considered a mutual magnetic field between coil 1 and coil 2 because it is produced by coil 1 and linked coil 2. The equivalent magnetic circuit of this magnetic circuit can be drawn as shown. As you may have noticed, the magnetizing magnetic fields phi M1 and phi M2 are added to each other because they are in the same direction. As you can see, the magnetic field phi M links the two coils. Basically, the magnetic field lines phi M is produced by the contribution of the two coils and can be called the equivalent mutual magnetic field lines. Now, if we apply the electrical network basics to the equivalent magnetic circuit, we can calculate the leakage and magnetizing magnetic fields as follows. Based on these magnetic fields, phi 1 and phi 2 can be expressed as follows. Now, since the magnetic field phi 1 links coil 1 and the magnetic field phi 2 links coil 2, the magnetic field linkages of coil 1 and coil 2 can be determined as follows. Let's discuss and analyze each of the magnetic field linkages at a time. Let's start with the magnetic field linkage psi 1. After substituting the magnetic field phi 1, the magnetic field linkage psi 1 will be equal to the following. The first term of the magnetic field linkage psi 1 represents the self-inductance and can be denoted by L11, and it is equal to the leakage inductance LL1 plus the magnetizing inductance LM1. The second term of the magnetic field linkage psi 1 represents the mutual inductance L12. Now let's give some details about the subscripts of the self and mutual inductances. Let's take L11 as an example. The first number of the inductance subscript represents the coil number, and in this case, it is coil 1. The second subscript number represents the current that produces the magnetic field that linked to coil 1, and in this case, it is the current I1. Now, I think it is clear why we call the inductance L11 self-inductance. Basically, it is the inductance of coil 1 and produced by the magnetic field generated by its current I1 only. As I mentioned earlier, self-inductance is always equal to two components: the leakage inductance LL1 and the magnetizing inductance LM1. These inductances produced because of the magnetic fields phi L1 and phi M1 that are generated by the current I1. In case of the mutual inductance L12, the first number of the subscript represents the coil number, and in this case it is coil 1. The second number represents the current that produces the magnetic field that linked to coil 1, and in this case it is the current I2. Basically, L12 represents the inductance of the magnetic field phi M2 that is produced by the current I2 and links to coil 1. Now let's discuss and analyze the magnetic field linkage psi2. After substituting the magnetic field phi2, the magnetic field linkage psi2 will be equal to the following. The first term of the magnetic field linkage psi2 represents the self-inductance of coil 2 and can be denoted by L22, and it is equal to the leakage inductance L2 plus the magnetizing inductance LM2. In general, L22 represents the inductance of the magnetic field that is produced by the current I2 and coil 2 and links coil 2. The second term of the magnetic field linkage psi2 represents the mutual inductance L21. Again, the inductance L21 represents the inductance of the magnetic field that is produced by the current I1 and links coil 2. Since L12 equal L21 and equal to N1 N2 over RC, we can represent the mutual inductance by a capital letter M. Therefore, the magnetic field linkage equations can be represented as follows. Based on these equations, the electrical equivalent circuit of the magnetic circuit can be represented or modeled as follows. This type of modeling of multiple coils is called a mutual inductance representation. It should be noted here that the equivalent electrical circuit of multiple coils can be represented by another way. This can be achieved by modifying the magnetic field lines equations as follows. The main difference of the modified approach is the simplification of the equivalent mutual magnetic field phi m to a new term equal to N1 over RC times Im. Now, based on the new calculated magnetic field lines phi 1 and phi 2, the magnetic field linkages psi 1 and psi 2 can be calculated as follows. After that, if we multiply the term of the current Im by N1 over N1, the magnetic field linkage psi 2 can be expressed as follows. Based on the final derivation of the magnetic field linkage equations psi1 and psi2, the electrical circuit of the magnetic circuit can be modeled as shown. This type of modeling is called transformer representation of the magnetic circuit. We will talk in details about this type of modeling during the electrical transformer lectures. It is very clear that the mutual representation and the transformer representation are different. However, these two different representations of multiple coils magnetic circuit give same results because they are developed from the same set of equations. I would like to mention here that the magnetic circuit of the two coils is considered a special case for the multiple coils magnetic circuit. This is because that the magnetizing magnetic field of this type of magnetic circuit is equal to the mutual magnetic field. Let's explain this statement by using the following two coils magnetic circuit. Now, if we focus only on the magnetic fields that are produced by coil 1, we can notice that there are two magnetic fields that are produced by coil 1. One magnetic field represents the leakage magnetic field phi L1, and the other magnetic field represents the magnetizing magnetic field phi M1 of coil 1, and at the same time it represents the mutual magnetic field with respect to coil 2. The equivalent magnetic circuit of this magnetic circuit is as shown. The magnetic field line equations of this magnetic circuit can be written as shown. These equations are similar to what we derived earlier, but this time the magnetic field lines of the two coils are opposing each other. That is why you see negative sign in front of the mutual inductances. I arrange this example in this way just to have additional possible scenario. As you can see, the magnetizing magnetic field produced by coil 1 is equal to the mutual magnetic field that links to coil 2. Likewise, the magnetizing magnetic field of coil 2 is equal to the mutual magnetic field of coil 1. The fact that the magnetizing and mutual magnetic fields are same is considered a special case. In general, the magnetizing magnetic field is defined as the magnetic field that links all the coils in the magnetic circuit, while the mutual magnetic field links only two coils. The definition of the magnetizing magnetic field can be clearly shown in a magnetic circuit that have more than two coils. Let's take an example. This magnetic circuit consists of 3 coils. Basically, this magnetic circuit provides a general idea to any 3-phase electrical machine winding. Now, if we focus only on the magnetic fields that are produced by coil 1, we can notice that there are 3 magnetic fields that are produced by coil 1. One magnetic field represents the leakage magnetic field phi L1, and the other 2 magnetic fields represent the mutual magnetic fields. The first mutual magnetic field links coil 1 and coil 2, and the second mutual magnetic field links coil 1 and coil 3. It should be noted here that coil 2 and coil 3 also have their own leakage and 2 mutual magnetic fields as well. Now, since the magnetizing magnetic field is defined as a magnetic field that links all coils in the magnetic circuit. Therefore, the magnetizing magnetic field of coil 1 will be equal to the sum of these two mutual magnetic fields. So, if we assume that the magnetizing magnetic field is represented by phi m, the mutual magnetic fields will be half of the magnetizing magnetic field. Therefore, the system equation of the magnetic field lines phi and the magnetic field linkages psi of the three coils magnetic circuit can be expressed as follows. Let's conclude this lecture at this point and we'll continue in the next lecture. I hope you found this lecture helpful and perhaps it will be useful to you in the future. I am Ihsan al-Nabi. Thank you for watching.